Okay, welcome back and welcome to the second lecture of the second week of the OpShin Pioneer Program. In this lecture we will look at how to do now. Previously we've done the on-chain part, we looked at the contract and compiled it, and now we will look at the off-chain part, how to interact with this contract, build a transaction that locks funds at the contract and then spends them again. So there are different ways to interact with smart contracts. One of them would be to use the raw Cardano's command line interface, the CLI. And this is how they do it in the Plutus Pioneer program. OpShin contracts can be interacted with any off-chain tooling. So you can interact with them using the Cardano CLI. And you can just follow the instructions that they use in the original Plutus Pioneer program to interact with the contract we have now written. So if you're interested in learning how to use the Cardano CLI, go ahead and have a look at the original video, which I will put in the description. However, OpShin was built to be very nicely integrated with PyCardano, which is a library to build transactions in Python. And the rest of this video will be looking at how to interact with the contract through PyCardano. So, right. First, we'll make sure that make sure that your setup is all there, that you have the poetry environment and that you're in the shell of poetry. So if I run poetry shell here, you will find that I'm still in the virtual environment that I was before, but for you it might look different. Anyways, make sure that you are in the shell of poetry. This is also something the PyCharm does for me. It automatically spawns my terminal into the shell. But for Visual Studio Code, you might have to run this command yourself. Then make sure that you have instantiated your .env file, like I have here. And navigate back to the root of the directory. And here you run Python 3 scripts create key pair. And I will just call it Alice, because usually in cryptography you have Alice and Bob, and Alice sends funds to Bob. So I will just call it Alice. And right, you will find it here in keys/alice.skey or vkey. And this address is a testnet address that you can fund directly. So for the different testnets, there is a faucet. So we are on preview testnet now. I will put the link to this faucet in the description. It's docs.cardano.org/Cardano testnets tools faucet. You can also find it by just Googling Cardano faucet. Then make sure to check.
Starting scheduled cleaning.
Oh. Second.
Pause.
That's my cleaning robot. Make sure to select the preview testnet, to receive test ADA, and then input your address. Make sure that you do this once and do it so you can only receive test ADA once a day by the default rate limiting. So make sure that maybe back up your keys and make sure that the funds are correctly sent. What I also often do is instead I set up a testnet wallet, a soft wallet in my browser, which is easier to manage, and then I send funds to the soft wallet, and then from there on fund my different shorter address wallets. So for example, you can set up Nami wallet, make it point to preview, then receive funds there, and then send them to your address. But I will just request it directly, and they will appear soon. Right. So back to this, we can check. Go to preview, C Explorer. I am just a light mode person. And now we already have 10,000 test ADA at this address. Very convenient. Right. So now we have the funds at our address. And now from this wallet, we will send the funds to the gift contract. And we have prepared already a script for this, which is called makeGift.py. It's built using the click command line construction. So what you have here is a function main, and that takes 2 arguments. The name of the wallet that you have created, which is Alice, the amount of Loveless that you want to send to the address, and then the lecture script address. And yeah. So I will walk you just quickly on what this code does. We load the chain context. You don't have to completely understand what this does, but feel free to look at the implementation. But essentially, PyCardano supports different ways to access the blockchain, Ogmios, Blockfrost, etc. And this will, depending on your environment file, generate the correct chain context. If you have not set up the environment file correctly, this might give you Ogmios when you don't have Ogmios set up, and you will get some connection refused error. So make sure to have your environment file set up correctly. Now we load the script info from assets gift testnet address. This is the address of the contract we want to send to. Then we load the address of our own wallet. This would be the address of Alice. And now we start defining a transaction builder, which is just a tool PyCardano gives us in order to make building transactions a bit easier. It's provided with a chain context. And then we can add inputs or input addresses and slowly over time construct transactions to submit to the network. So yeah. Our input address is the Alice wallet. So we tell the builder, if you need any funds, just go to this wallet and take whatever whatever UTXOs you can find, and take them as inputs. Then the datum is Plutus data, which is actually not the unit type as described here, but something different. But we can use unit if we really want the unit type. That's pycardano.unit. So this is of type Plutus data, and it has constructor ID 0 and nothing else. We'll find later that we usually want to have Plutus data with more information with different fields, but here there's really nothing inside. And then we instruct our builder to add an output to exactly the script address with the amount that we specified, which is 3 Loveless here. You can also specify native assets and so on. We will look at this later, but integers will just put Loveless. Loveless, by the way, 1 Loveless or 1 million Loveless is 1 ADA. So it's the integer math that the blockchain does internally. So when we send 3 million Loveless, we actually send 3 ADA. And this will be what you see in the explorers or in any user-facing interfaces, but this is for developers, it's in millions. And then we load the verification key, the signing key, and again our address from our wallet. This is the secret key that the blockchain needs a signature from to authenticate that we are indeed able to spend funds from this. And then we build the transaction and sign it, and with our keys, send it to the address, and then submit the transaction. And here you can change this link, whether you're working on preview or preprod or the Yahtzee Explorer. Just change this link to give you the transaction hash that you want. So let's go ahead and run this. Yeah, need to go into source week 2 and then make gift. Then you supply an argument, which is the Alice wallet, and we have submitted it. Let's have a look. And might take a while to show up. Nothing yet. We give it a few seconds to synchronize. This is usual because there's only block production every 20 or 40 or 60 seconds. It might take a while for a transaction to actually end up on the C Explorer. There we go. And now we can see we send funds from this address. This is the address we put here for receiving the ADA. That's the address. There's one UTXO here with the 10,000 ADA we received from the faucet. And then there's an output with roughly 10,000, but actually if you look closely, it's 9,969.83. And one output of 3 ADA, which is the 3 million Loveless that we specified. And it sends to this address, which is a smart contract. And it attaches datum. As I told you before, UTXOs can have a datum attached, which is the state. And for this contract, we don't really need a state. So if you look at the datum, you will find that this closely resembles actually the definition of the unit, which is constructor ID is 0, and then there's no fields. So there's different representations for all of this. You can also look at the CBOR directly, for example, using this tool, and then you will see there's a tag that's usually like 121 plus the constructor ID, and then there's the fields. So yeah, as we will see, there's many different ways to look at datums, and we have just submitted our first funds to the gift address. Right, now we have sent funds to a contract, which is usually the easy part, because the blockchain doesn't check whether the datum that you attach makes any sense. It will just let you send whatever to a contract, and there's actually also no contract being run yet. We just initialize the contract with the state, but the contract itself doesn't have to run when you send funds to it. This will change now in the collect gift script. So here again we specify a wallet, and then we specify a contract from which we want to get the funds. You will see some repetitions here. Now we define the context, we load the context again with the same function. Now we actually load the contract using the gift script CBOR. This is the actual contract code, and we collect it by reading script.cbor, and this is hex representation. This is not actually bytes, so we convert it into binary by running bytes.fromHex. You can also alternatively load the script.plutus, access the CBOR hex, and then you have to unwrap it from its CBOR. It's like bytes in CBOR, which we have to unwrap. CBOR, it's concise binary object representation, some format we use to wrap contracts, to represent transactions, to represent Plutus data, all these things. So yeah, there's an alternative way to do the same with .plutus files, which you, for example, get from PlutusTX, but I don't go into much detail here. Much more easy, and also provided by most modern frameworks, is script.cbor. Then we load the Plutus v2 script from this, hash it, and by putting this hash into the payment part of an address, we get the actual address of the script. And you can actually verify it yourself, but the address that you get from this procedure is the exact same as what's provided here in the testnet address. So yeah, that's what's happening in the background when OpShin compiles. It computes this hash and the script cbor, and then wraps it, hashes it, and wraps it in an address, and that's what you get as an address. So yeah, as I said, alternative to this is also to just load the testnet address directly. It will give you the same, should give you the same thing. Now again, we load our address, our wallet, and what we do now is we want to spend funds from the contract. So what we do is we iterate through all the UTXOs, all the states at the contract address, and we check that the datum matches our expectations, that they're in a state that we expect to be able to be spent. Now, for the very basic gift contract, there's not much to check here. We just need to check that there is a datum, because if you send funds to a contract and there's no datum attached, you can never unlock them. That's part of the ledger rules. So yeah, if there's a datum attached, we will get, we will in this case already say, okay, then it's good, then we can spend it. And we, yeah, in old frameworks, you have to provide in a collateral UTXO explicitly, going through all UTXOs, and collaterals shouldn't have any NFTs. You basically provide them as a collateral if the transaction is some technical part of the blockchain. If the transaction manages to make it on the chain, gets distributed, but actually turns out to be invalid, you want to reimburse node block producers for having had to look at this transaction, so they can collect this collateral. And there's, as of the most recent fork, this is not necessary to add upfront anymore. So there's something called collateral return, which just says, okay, take anything but my return if my transaction happens to fail. So we can actually remove this part, but it's yeah, feel free to look up the meaning of collaterals. Now, right, we are in the gift contract path again. The gift contract ignores the redeemer entirely, so we can just put whatever. We can put a unit, we can put just 0 or empty bytes, or we can even put something more complex, but we'll just put 0 for demonstration purposes. Then we define the transaction builder. We add, okay, and now we add a script input, which means the UTXO we found at the script address. We figured, okay, this is the one we want to spend, and this is the script that we're using, that the node will have to run to spend it, and this is the action that we want to perform on the contract. Again, there is no real action for the gift contract yet, but we will specify it nonetheless. And why do we have to provide the script here? Is because when you send the when you define the address, it's just the hash of the contract. So the chain does actually not know what is the corresponding contract for the hash. So yeah, we provide at this place the Pluto script. So the node will go hash the script, check that the hashes match, and then run the code that you provided. Again, we don't need collaterals. Then we sign the transaction and submit it, and this is the same now as before. And let's run this. So collect gift. Again, we provide the Alice wallet. This takes a bit longer to execute, and let's have a look. There we go. Now, you can see the input here is our input from the contract with the datum. And now we can also see that there's a redeemer. That's the action that we provided. And okay, this is the contract that we executed. We can also see this here now in the contract script. Now we actually performed a script on chain. Like the node ran this contract and validated that it's able to spend the funds. So you can see the whole contract. You can see the hash of the redeemer and also the redeemer itself. In this case, it's really just an int 0. Could be more complex, but we just provided 0 if you recall. So this is just int 0, and then there's a script hash. And you can also see how many steps and memory it cost to run this contract. Right, you cannot. Yeah, here is int 0, the redeemer. This is the contract, the entire contract, and this is memory, steps, and fee. This is how expensive it was to run this contract, and you will find later that this grows quite a lot as our contracts get more expensive and complex, and we will spend most of our time then optimizing to make the scripts as small as possible. You can now also see that there's a collateral part here. Even though we didn't provide the collateral, PyCardano provides a collateral for you, and that's just the entire input that we had. It's not spent or anything. It's just there. It's part of the contract it's part of the transaction. So that's why it's displayed here. And then another script tab which just shows you, okay, we ran this Bluetooth contract. You will also find that different explorers display different detail. Like they all display the same transaction, but actually they display different detail. So here it's presented a bit differently. You see that, okay, this is a summary of the transaction. Now, again, this is what we see on C Explorer as well. The singleton UTXOs, which number was sent where, and then here you can also see this is the seaboard data, this is the datum and the datum hash, this is contract. And here you can actually see in more detail what this collateral was that we provided. It's as input 9996 ADA and as output 9993. So actually, if the transaction had failed, the node would only be able to collect these 3 ADA, and the rest would have to go back to the owner. That's specified here. And that's just a detail. So yeah, that's all for the very basic contract. If you've made it here, you've successfully managed to run a script on the chain. This is just testnet, but still. And yeah, you also, if you have looked at the Cardano CLI version, you also now know 2 ways already to interact with smart contracts on chain. And we hope that you see how PyCardano is more convenient, and because it's directly scripted and you can interact with the contract using our definitions. Anyways, you will also want to have a look at Lucid or Translucent or our modern JavaScript transaction building frameworks, because these can be used in dApps, in the front end, and so on. Anyways, that's it for this introduction, and see you for the next lecture soon.